Today, to start with, I just want to quickly revise sketching Qubit graphs. So can you try and sketch in A, B, and C, finding out, first of all, where the functions intercept the x and y axes? Okay, hopefully you've paused the video and had a go at that. So A looks a bit like this. You can factorize out x straight away to create a quadratic. It's going to be x squared plus x minus 6. And then that will factorize into x plus 3, x minus 2. So that's where we get the minus 3 from, the plus 2, and obviously the 0 from taking, actually not obviously, because it's quite easy to miss this one, but the 0 from taking the x out. And we also get that the intercept is 0. Okay, the next one's a little bit trickier and actually have to try some numbers. You have to use the factor theorem and try some numbers. Wait, try some numbers is just one method anyway that perhaps you used. But because we've only got a minus 2 here, you only have to try numbers like 1 and 2 and minus 1 and minus 2. And those will be the only ones that could work if it was to factorize nicely with integers. It turns out that we're going to get x plus 1, x plus 2, and x minus 2. To be honest, I've read this by looking at the roots on the graph, but wait, that was not quite right. X minus 1 there, sorry. And that gives us the roots of 1, minus 1, and minus 2. And in this case, we get an intercept of minus 2. That's what it looks like. The last one is the trickiest one, and that's because it doesn't actually factorize. So the only way really to do this one is to notice how it links with B. And all it is a translation by minus 1 in the negative y direction. So you may or may not have spotted that, but it's once you've got that, you can take the graph and you can just move it down minus 1. And there's actually only one root, and it's not going to be very nice. It's going to be a bit bigger than 1. And to be honest, this is the starting point for today. How could we solve this equation equal to 0 effectively? Well, we could try and find a sign change. We could do a decimal search, but is there a quicker way of doing it? And the answer is yes, there is. This quicker way is called fixed point iteration, and it is magnificent. It has its problems, which we'll talk about, but basically we're going to be finding roots by this thing called fixed point iteration, which I'll explain. And it's more efficient than a sign change rule, and we're finding these roots numerically, remember. It's not exact, but we can find it to any degree of accuracy that we want to by iterating. That means, we're putting it into a formula, and then we're putting that thing back into the formula, but all will be revealed. Okay, to start with, you might want to think about this. You might want to pause the video and think, like, how do calculators actually work? How can you find the square root of 7, for example, on a calculator, and it give me the answer of 2.645 and the like? How does it know that? Does it just have it stored in its memory? Does it have a square root of everything? And I don't think it does. Actually, I don't know how all the functions work on a calculator, but I do know how I could construct a square root function. I'm going to show you. I'm going to just ask you to do this to start with. We can actually use the following formula. So what I'd like to do, I'm going to go with the square root of 7. So I want you to try out the square root of some number, probably not a number like 4 because that's going to give an exact answer, but one that you'd get an inexact answer for. And then start with an approximation. So I think the square root of 7, well, it's going to be more than the square root. It's going to be more than 2 because 2 squared is 4, but it's going to be less than 3 because 3 squared is 9. So maybe I just start with 2.5. I'm going to then press equals, and what that does is it actually stores it as my answer button. So now, if I do 0.5 or a half, as I've got on the screen, 0.5, and then the answer button, plus 7, because that's the number I want to find the square root for, divided by answer. Okay, then at the moment it's using answer as 2.5. I press equals, I get a new number, 2.65. Now that becomes my answer button. So if I my answer in my memory. If I press equals again, it will use that in the formula. So this is a way of very quickly doing iterations. And if I keep doing it, oh, I've now found that it's got stuck, and lo and behold, it's actually the square root of 7. Amazing. If I square it, what's going to happen? I'm going to get 7. Okay, little smiley face there. This formula allows us to find the square roots. The thing is, how is it doing that? And you can try. I didn't. That wasn't just a trick. Hopefully you tried a different n and you got a similar kind of result yourself. And even if you started with like really far away, this method still works. So let's say I think the square root of 7 is 86. I'm laughing because it's obviously not. But if I do it, the same formula. Okay, I'm putting 86 in as answer, right? It's gone to 43, 21, and it's very quickly still going to that answer that is the square root of 7, okay? It's just obviously the closer I start to the actual square root of 7, the quicker I'm going to converge to what I want. So what is going on here? And actually what is going on is a form of fixed point iteration. What we have just used, and I'm kind of assuming you've seen iterative formulae before, but this is what we've used, this iterative formula here. We've put in a value, and then we've done an operation and we've got a new value. So, but it's all in terms of n. So for example, if I put in x1 was 2.5, then x2 would be, I would let n equal 1, x2 would be a half of x1 plus n over x1. But then x3 would be half of x2 plus n over x2, and so on. And I just keep getting more and more of these x's, and what is going to happen is it's going to converge to my root. So that's just a very quick explanation of what an iterative formula is. I think we've seen them when we've done sequences, like the Fibonacci sequence is actually, and we've looked at recurrence relations. It's the same idea essentially. So the Fibonacci sequence is defined like this. This one of the sequences found by adding the previous two, and then you might say that the first one is equal to 1 and the second one is equal to 1, and off you go, you've got your sequence. Okay, same idea here. Right, where has this iterative formula come from that I've circled here? What we're actually doing is the following. We are trying to solve x squared equals to n, which gives us that x is the square root of n. That's what I wanted to find. X is going to be bigger than 0. We're ignoring the negative square root. What I can do actually is a very clever series of manipulations. So I can say that x is equal, like why do I want to do this? Well, it will become clear. I'm just saying that we could do this mathematically. I could divide through by x to get x equals n over x. I could then basically multiply, well, I could add x to both sides actually. That's what I've done on this next step. I've added x to both sides, and that's given me 2x equals x plus n over x. And then I've divided through by 2, and that's got the formula that we've just used. And then I've turned it into an iterative formula. So actually, this equation that I'm now circling is identical to the equation x squared equals n. I've then turned it into an iterative formula, and that's, I think, the bit I've not yet explained. Okay, what we're going to do is we're going to look at a graph made by GeoGebra below. And you can actually use a graphing software to kind of, get different graphs up for different n and the like. But anyway, okay, so what I am doing, I'm going to draw a graph of y equals x and y equals a half x plus n over x. So I've basically turned it from being an equation in terms of x to sort of simultaneous equations where graphs cross. We do it the other way around sometimes, but anyway, these are the same thing. I'm just going to highlight this. This here, solving for x, is the same as finding where these two graphs intersect. what we get is the following graph. The one, so, oh yeah, I've written it on there. The one in red is y equals a half x plus n over x here. And then the black line is y equals x. And I've used an equal aspect scale here, so it should be 45-degree angle there. Right, what is going on when I use an iterative formula? Okay, this is the bit, I just need to take it slowly and explain this. So when we put our first value of x in, let's say, so I'm not going to go with 2.5 or 86, or I'm actually going to do the square root of 30 as well. Just, not sure why I did that here, but you can do it for any square roots. All the graphs will look kind of similar. Might be a good idea to, here we go. So here's GeoGebra open, and actually you can see as I'm making it 30, it moves up like that, but all the graphs kind of look the same. They're just slight modifications as I change n. And actually, it doesn't matter what my starting guess is. Sorry, this will make more sense in a minute. Let me explain the graph. So what is going on? I'm basically putting a first value in. So this is my x1, and that's equal to 24. And then I'm substituting it in and finding out what like this bit would be, a half xn plus n over xn. Okay, so that's this value here. This value that I put here is what happens when I put x1 into that formula. Now, what do? That becomes my new iteration. So actually, at the moment, that's my y value, but what I do is I go along the graph to where y equals x is, and I make it my x value. So that this value here, question mark, is exactly the same as this x value, question mark. Okay, let me just say this again. x1, I've gone up, I put it in my formula. Okay, I've got a value out, and then I've made x that same value. And the way I've done this geometrically is by taking it along and letting to where y equals x. That's what I'm doing when I let x be the new value. I then put that into the formula, and then and then this is what I get. And then I let x be my new value, so that's me going along. And if I do the same again, I've got this iterative thing, and as you can see, it's actually converging upon where the graph intersects, which is exactly what I wanted. So this fixed point iteration, I think it's called fixed point because this point is fixed, but I'm doing these kind of like jumping around things. That's not very technical, but that's what I'm doing. And as you can see, if I change the value of where I start, then yes, the path changes slightly, but it still goes towards my destination where I want to, this value of the root. If I change the value of the root that I'm interested in, then the paths change again, but I still get there. So I hope this makes sense. What we are doing here is we are able to take square roots of numbers using an iterative process, and calculators are very good at iterative processes. We're just like doing some basic addition. So hopefully that makes sense how a calculator could take a square root quickly. Not sure if that is the method used, but that could be a method used. And we've constructed a formula, and there we go. So we can use this idea to solve any equation actually, and we're going to see that there's some downfalls to it, but actually the process is there. If we can get a formula where x is equal to some function of x, then we can use this iteration and go along little lines like we've done here and get an answer. So as long as we start with a formula that we want to solve and we can get it in terms of x equals f of x, then we are sorted. Here's the technical bit of the lesson then, iterations. If the sequence given by the recursive definition xr plus 1 equals f of xr, that's what I was talking about trying to get it in the form in, with some initial x0, if it converges to a limit L, then L is a root of the equation x equals f of x. All this is really saying is, if I get to a fixed value, because it will turn out you don't always get to a fixed value, if you get to this fixed value, then it will solve the equation x equals f of x. And as long as you can rearrange x equals f of x back into like the equation you want to solve, then you've solved the equation. That's essentially it. So this is a little task for you now. This again is the cubic that we saw at the start of the lesson. It was that more horrible one where I'd translated a cubic, and we can see the root is 1 point something. How could we figure that out using using this fixed point iteration? The process will be similar for solving other things like involving exponentials and logs and the like. And what I want you to do is pause the video and think, how could you rearrange the equation into x equals f of x from here? And there's many ways. There's not just one way, because it doesn't have to be this x as the subject. Maybe I could make some, maybe I could make it x equals some other function of x. I want you to have a go at this. Can you think of like 3 or 4 different ways of writing it? Pause the video and have a go. Okay, now I suspect that maybe you wrote this one down. X equals x cubed plus 2x squared minus 3. That would be one way of doing it. I've definitely made x the subject. I've just added x onto both sides essentially. Another one you might have written, maybe you wrote x cubed equals 3 plus x minus 2x squared, and then you took a cube root. That would have worked as well. And actually there's so many ways we can do it. All these different ways would get an equation x equals f of x. What you then should do is try and see if it will work. So I think I'm going to start with x, the cube root one. I can see that the root's going to be quite close to 1, so maybe I try 1 as my starting point, and then I do the cube root of 3 plus my answer, which is 1 as my starting one, minus 2 times my answer squared. Let me just backtrack. I've essentially turned this into this iterative formula. X n plus 1 equals the cube root of 3 plus xn minus 2xn squared. That goes to there, because that's what we did before with the square root one. I went from this green highlighted one to that one. Okay, if I do that, I'm expecting to get about 1.1, 1.2. Let's see what happens. I get 1.25. I just keep pressing equals. Okay, it's actually kind of flipping between things, but it is, oh dear, it's taking some time. But you can see in this particular case, it's taking a long time, but it is slowly converging. If I just keep pressing equals, then I'm getting there. I've got 1.147 fixed, and if I keep doing it, I will get there. Okay, so that's going to be my answer. If I was to put it back into this equation here, I would expect to get very close to 0. Okay, let's see what happens if we put it into the first equation that I said. So the same again. It's going to be 1. No, wait a minute. I went with 1 as my starting point, I think. Okay, this time it's going to be answer cubed plus 2 answer squared minus 3. Okay, what happens this time? Goes to 0. Oh dear, oh dear. Actually, we've not converged to exact value, so we've not done anything kind of wrong. It's just the sequence doesn't converge to a limit, and therefore we're not able to get the root this way. Now the question is, why did that not work? And I've got some graphs to show you. So you might have come up with some of the other ones. This one top left is the first one that I did, and this is what's actually happened. So when I put my number in, it actually kind of spirals around. So I'm just going to talk about this again. So I put in my value of x, I find the value of the function, that becomes my new value of x. I find the value of the function, that becomes my new value of x. I find the value of function and so on. And due to the nature of this shape, it kind of spirals around and it takes a long time to get to the root, which is exactly what I found. So it works, but it's a bit slow. What do you think we might call this kind of diagram? Okay, spoilers. It's actually cool. What does it look like? Like if I draw a little creature kind of wandering around, that's meant to be a creature. It's actually called a cobweb diagram because it spirals around and looks a little bit like a cobweb. One other thing I could have done, another thing that I could have done is I'm just going to talk about where this formula came from because I've not mentioned it. I could have made 2x squared the subject and done 2x squared equals 3 plus x minus x squared if I rearrange this formula here. Then I could have divided by 2 and then I could have square rooted, and that is what this formula here is doing. And it seems to be a quicker way. There's less spiraling around. It's still a cobweb diagram, and the graph looks different, but I'll get the same answer at the end of the day. So it's a different iterative formula which gives exactly the same answer, the solution to this cubic equation. Okay. Now, what went wrong when I put it into the second one I did? Well, this is what happens. Just due to the nature of the graph, when I put it into the function, because the function's kind of this cubic and is going up to infinity really quickly, then actually it just hops off and goes to infinity as well. Okay, not to where we wanted it to. So basically it won't always work. That's the problem with this method. You might make an iterative formula that just doesn't work, but you can kind of find, you can test it and you can find out and then you can come up with another one. I think, like, my understanding is generally, you want to be trying to take cube roots and square roots because then you don't get things going off to infinity like this. You can see the nature of the graphs, it's not going to be problematic, whereas the nature of this cubic graph is it is. Now, I guess the good news in some respects is that in A level, I'm pretty sure, 99.9% sure, you won't be asked to, just come up with an iterative formula. It will be a question like show that. It would say, show that if x equals x cubed plus 2x squared minus 3, then you can rewrite it into this iterative formula here. So you kind of at least know that you're going to have to square root at some point, so you're probably going to make x squared the subject to start with. But having the understanding of when some work and when some don't work is what I want to talk about today in addition to this. There's one thing I forgot to mention. It's frustrating. Okay, this one was a cobweb diagram, as was this one. This one doesn't really, I'm not sure this one really has a name since it doesn't actually lead to a solution. But it kind of looks like the same as this one, except this one does go to the solution. Now, what is going on here? It's not, you don't tend to get spider webs look like this, but sometimes when you wake up in the morning, you walk along and maybe you go down some stairs to get some breakfast or something. This is called a staircase diagram. So main learning points for today is that we can solve equations numerically using iterative methods. I've tried to explain how it works. I've distinguished between cobweb diagrams and staircase diagrams. You should be able to draw them yourself using the ideas I've talked about. If it converges, if the iterative formula converges, then you do get a root to the original equation. If it doesn't converge, bad luck. There are lots of other ones that you might have found that do also work. I just picked some of them, I want to say like the more obvious ones, but you could, there's other things you could have done I'm not going to go into here. So you can normally find the root to any degree of accuracy by continuing the iterations until the required decimal place has been unchanged for 2 or 3 iterations. What I mean is, if I've lost it here, that other formula I got where it was taking a long time to get to, what I really should do to be absolutely sure that I think it was 1.471. To be really sure that it was that to 3 decimal places, I should just resort to the sign change rule and did what we did last lesson. Look at 1.405 and 1.415, and if I get a sign change between these two, then I know that it's going to be, I've messed this up, but like the method kind of work. If I want to show that 1.41 was the root to 2 decimal places, then I should look here and here. That's the point I'm trying to make. So we're coupling in ideas from previous. It's not like we just forget those. The sign change rule is still a useful thing, but fixed point iteration is the key thing we want to now sort of be able to use to find these roots more effectively. We don't want to be doing decimal searches to get things to 6 decimal places when a good iterative scheme can do it really quickly for me. Okay, let's try a couple of questions. What I'd like to do is pause the video, have a go, and then look at my solution and see if you agree. Part A. Show the equation f of x equals 0 has a root in the interval 3 to 4. This is sign change rule, what we did last lesson. So find out what f of 3 is. -1. Find f of 4. (13). F of x is continuous between 3 and 4. I would always just write this down because that's that condition that if it wasn't continuous, it wouldn't mean that there's a root. There's a sign change. And just a conclusion, so there is a root between 3 and 4. Okay, nice one. Right, now we're given an iterative formula here. We're actually not expected to understand where it's come from. It's just a case of substituting in. But let's talk about it anyway. So this would come from making 3x squared the subject and then dividing through by 3 and then taking the square root. You might want to play around with that to see if you can get it, because in some questions that will be expected. But here we don't need to, we just need to substitute in. So we need to find the values of x1, x2 and x3. So let's set it up. So 1.5 is my starting value first of all. Square root, fraction, what does it say? Give my answers to 4 decimal places throughout. So 1.3385, 4 decimal places is going to be 1.3385. (1.2545). Just be really careful with the rounding. x3 1.2200. Okay, there we go. If we did press equals, then actually we see it kind of hops around and it goes back up a little bit. Okay, good. So that's going to be a root because it converged. I mean, it doesn't actually ask about that, but that would have been the case. Okay, part 2. Different starting value. Is it going to matter? So actually here, unfortunately, I think I'm going to have to do exactly the same again. 4 equals, and I don't think I can get back to that formula. Maybe there's a way I can, but I don't know. So sorry, I'm going to have to do it all again. Okay, this time 4.5092. .4058. In an exam, probably best to write a few more decimal places down and then round it. You won't be penalized if you round it incorrectly, whereas if you just round it incorrectly and write it down, you will be penalized. I'm doing it maybe a bit lax here. 7.1219. Okay, and actually this doesn't seem like it's going to the same root. If we keep pressing equals, it diverges. Wow, so this is different than previous because you might get an iterative formula which converges for some starting values but diverges for other ones, which can make it, this can make the method, you can see some of the issues with the method. And furthermore, if I plot the graph of y equals x against this function, the square root of x squared minus 2x plus 5 over 3, I in fact find there's 2 solutions to the equation. That's possible. Actually, there may be a solution that I've lost. Since it's a cubic, you can only ever have 1 real solution or 3 real solutions. So this graph has lost the negative, I think, because we're taking the square roots. In any case, we've got 2 on there. Now, what I've asked is illustrate both iterative paths on the diagram. I just want to show you to demonstrate some understanding of what is actually going on. And this will help, I think, understand why one diverges and one converges. So if we started at 1.5, well, this is about 1, so it'd be roughly here. Then when I substitute my 1.5 in, here I go up to here. If I then make my x value the same, then it's going to go along to here, and you can kind of see straight away, like I can't really illustrate on here how it's spiraling around because I'm not zoomed in enough, but it would spiral in, or maybe it wouldn't actually. Maybe it would just be a do you know what, I think it would be a staircase diagram, but I would get to the solution. If I started like here, it would be more clear to see how it's going in, because it would go like this, and you get something like that going on. Okay, but I just wanted you to demonstrate roughly what's going on, because let's look at what happens if we start with 4. Okay, now I go here, I get the function, then I make x the same value, so I go along, I'm like bouncing along really, and then I'm going to go up, and you can immediately see why it no longer works, because so it's just this actually small range of values where it would be convergent. Here it's divergent. Bit extra to the question, but I want you to have this understanding. I have seen it on exam questions actually, where they've asked drawings of part of cobweb and staircase diagrams, and having this understanding of what is going on, when it converges, when it diverges, just having a feel for it. It's not, I don't know if it's an exact science. Like, how would you know, by constructing this, when it converges and when it diverges? That seems very difficult question, to be honest. In our case, we just need to be able to substitute it in, but we can see that it does diverge in some places and does converge in some places. Okay, second question. So this time we are being asked to show a rearrangement. Okay, for a root, it's going to be that x squared minus 4x plus 1 equals 0. Show that it can be written as this. Well, I've got 4 still in my equation, and I had 4x here. So for me, it's probably going to be the case that we're going to divide through by x. X minus 4 plus 1 over x equals 0. And now I can see I can rearrange it to x equals 4 minus 1 over x. So just when you get this sort of equation, look at what your starting thing is, look what your final thing is, and think, like, what am I going to have to do? If there's no square roots involved, then obviously I'm not going to be doing any of that. Just, you know, it's just a process of practice and understanding. So we've done that, and then we're told it has a root between 3 and 4. We don't have to do a sign change, but we're asked to use an iterative formula. So I'm given x0 is 3. I'm just going to write that down. Now it's exactly the same as what we did before. Okay, so 3 is my starting value. And then I'm going to do 4 minus. This is very. I haven't used the fraction button here. This is, you know, this is a quadratic actually, and we can solve this exactly, but it still, you know, kind of illustrates the process of iterative methods. So 3.6 recurring. Actually, it doesn't tell me to round it in this case, so I'll just leave it exact. 3.72 recurring. And 3.73 is it 130, 170. Don't know, maybe it wants me to round it to 3 significant figures. 3.67. Maybe I'll just do that as well. It doesn't say.